So far we have been looking at linear function approximators. Linear function approximators are somewhat restrictive, right? I mean, we won't say very, right, or somewhat restrictive, right? And they can model obviously linear functions of the weight vectors, and we have to put in some thought into designing what the feature function should be if you want nonlinear functions in the original inputs, right? And while nonlinear function approximators can directly model more complicated relationship between functions, and even though you could start with a set of phi, I could look at more combinations of these feature dimensions and to come up with more complex functions. And in fact, as we will see later, you can set it up so that the phi functions are actually learned, right, and can generalize more effectively to states that are unseen, because linear function approximators typically make this linear extrapolation, therefore suffer from all kinds of generalization issues, especially beyond the edges of what you have seen, right. Of course, the biggest disadvantage is most of these require a lot of data and significant compute power just to compute the the more complex gradients and also do the updation, right. So we'll look at it, obviously this is the state of the art, right. This is the direction the field is moving in. So we'll look at a little bit more of this, right. So the first thing I want to talk about is to step back, take you back to the backgammon player. So how did Jerry Tesaro design the backgammon player, right? So all of you remember this, we talked about Jerry Tesaro's, that's Jerry. We talked about Jerry Tesaro's backgammon player, right, in the very first lecture, right. We said it is like this game, right, where you have this pieces like this is a game like Ludo, right, where you have these various pieces and then you roll the die, and based on the die movement you move the pieces around, and your goal is to get the pieces off the board as quickly as possible. Because there is this stochastic die roll and because there are so many pieces on the board, this requires some amount of strategizing, and classical AI approaches had trouble playing this game well, right. And then Jerry came up with this TD-Gammon, right, and that said that could beat the best human player back in 1995. They had this championship matches and things like that, and a bunch of different things we talked about. It learned completely by self-play. In fact, Jerry was the first person to think about this and introduce this whole notion of self-play. Now it's pretty commonly used elsewhere, and of course this is the advertising bit, right. So it actually learned to play things in ways that humans hadn't thought about, because it was actually playing the equivalent of like 1.4 million games or something. No human actually plays 1.4 million games, right. So the fact that it just played so many games because it was playing by self-play allowed it to do well, right. So how did Jerry represent the value function? That's what we are interested in, right. So what Jerry Tesaro did was actually represent it using a neural network. It's a non-linear function approximator, as you know. So with sigmoid hidden units, he varied the number of hidden units. So somewhere between 40 to 80, there is just one hidden layer, right. So inputs going to one hidden layer and going to a single output linear activation layer, linear activation neuron that was giving you the value of Vt. Vt is the value function corresponding to the input state St. Right. So that was basically it, right. And so the way Jerry did this, the reason Jerry did this is the following. In fact, it was not very thought through in terms of a deep manner and saying, oh, I need to have a linear function approximator, non-linear function approximator and things like that, right. So in the late 80s, early 90s, there is this algorithm called Neurogammon, right. So Neurogammon was again developed by Jerry Tesaro. It used the exact same architecture, right. It used the exact same architecture in terms of the neural network, and so he had trained it using supervised learning. So what had he done? If you remember, I told you he trained it using supervised learning, where he came up with the expert moves. Given a board position, he said, okay, this is the move that you have to make, right, and then so it basically learned to make the moves, and the neural network itself was trained using some kind of a supervised loss, right, training loss. Right. And then it did well, like we said earlier. It played at a medium human player level, because that is the level at which Jerry was, and it was not really doing great amounts of generalization. And remember, it was not doing much of a look ahead search or anything. So given a board position, it learned to predict what the next move should be, right. So that's basically what Neurogammon did. And for developing Neurogammon, he used this multi-layer neural network. So he said, oh, I'm just going to use a multi-layer neural network because I know, right, this network, right. And then he set it up, and he trained it using TD error this time as opposed to supervised learning error. And then he came up with this game player that kind of blew everybody out of water, right? And for a long time, this was the only successful RL application with the neural networks, right? All the others with a complex neural network, right? I mean, people had done it with 1 or 2 neurons, but with more of this kind of a multi-layered perceptron architecture on a non-trivial problem, right? For a long time, this was the only successful story, and most of the other success stories were using Cmax or other linear function approximators, right? So, what did Jerry use for phi, right? So, Jerry Tesaro used this kind of a 198 dimensional input vector. So, basically it is a phi that takes in the board position, right, and gives us output a 198 dimensional vector. Right. And this 198 dimension vector was fed into the neural network, and then it went through all this computation, and then finally it gave you the output, right. So, this was turned out to be, this is a very crucial component of this, right, and this 198 dimensional input, it's not just like a snapshot of the board. It's not like saying, okay, how many pieces are there in the first location, how many pieces in the second, how many pieces in the third, and so on and so forth, right. It had a lot more game knowledge thrown in. So, for example, in backgammon, apparently it is important for you to have multiple rows, right. So, rows occupied by multiple locations, consecutive locations occupied by 2 or more pieces of your own type, right. So, let us say 2 blacks here, 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 and so on and so forth. In each of those locations, you need 2 blacks, right. So, what happens is, if a white piece comes here, if there are 2 pieces in a position, you can't cut it, right. So, the white piece is essentially blocked, right. So, if I have 5 2s in a row, 5 2 pieces in a row, the white has to throw a 6 to move past this, right. It is kind of like a blockade, right. And if I have 6 of these 2 pieces in a row, basically I am stuck, right. The white can't go past me, right, because the die throw roll goes from only 1 to 6. So, the white guy is stuck on the other side of my blockade, and as long as I can keep them there for a long time, right, keep them on the other side of my blockade for a long time, then I have improved my chances of winning. So, what this 198 dimensional vector will say is, how many of these sequential things do you have? Do you have 4 of these? Do you have 5 of these? So, that way you can say that, okay, this is a better position. So, if I go to this position, I am slightly better off than a position where I had only 3 of these in a row. If I go to a position that I have 4 in a row, so I am better off, right. So, I could do these kinds of comparisons. So, this kind of game information, right, knowledge about the game was encoded into this 198 dimensional feature vector, right. So, putting things together. So, for the backgammon, we did a non-linear function approximator so that you could generalize more effectively, right. It was trained using TD learning. The output was a linear neuron. So, it could you think of a similar loss to the linear gradient loss that we talked about in the previous slides, right. But the true thing came here because he used a feature vector. The phi vector was 198 dimensions long, and that got fed into the neural network. The same 198 dimensional features that Jerry Tesaro developed for Neurogammon. So, it used the same set of features over here, but the whole training here was done through TD error, and it did way better than what supervised learning could do. Okay, this is great. So, what about Atari, right? So, we talked about the Atari game also. We showed you some videos where it learned to play, right, from scratch, right. That was really amazing stuff, right. It learned to play from scratch. What was amazing about this learning to play from scratch is that the features also was learned from scratch. You didn't specify what the phi was, right. In fact, when the agent looks at this board, right, when the agent looks at the board for the first time, all it sees are a bunch of pixels, right. The agent doesn't know when it makes an action, the green pixels here are the ones that move, right. Even that it doesn't know. It has to kind of somehow infer that, right. It never ever really has this notion of I am controlling those pixels, because that is not there in its lexicon. So, it can't learn a concept like that, right. But it still learns, okay, if I If I go up, then I go to a better state or a worse state and all that, right? And likewise, it has these pixels, right? That white pixel that's there in the middle, and that is the ball, right? It doesn't know, right, that it has to hit the ball. So that's why initially, if you look at it, if you remember the video, it was just sitting at one end, not moving at all, right? Until it started some explorations and started moving around. So it was really learning from scratch. But what was amazing about this whole thing is nothing was told to it, right? Its fee was essentially a random. Initially, it started off with some random initialization, right? So maybe in Pong there is nothing much to look at, but if you look at something like Space Invaders, there is a lot more features there in Space Invaders, right? So it could potentially have been learning much more features, right? Somebody could have told it things, right? So in fact, the level of how from scratch it starts, right? The tabula rasa learning, it doesn't even know that all these yellow pixels will move together. It doesn't even know that these are objects that are moving together, right? It doesn't know that this green one is moving, and when it has to aim to fire something. So all of these things are learnt only purely from exploratory behavior. So in some sense, you can think of it as very inefficient way of learning, but also you can look at it saying that, hey, look, that is a way to learn everything from scratch, right? Whether that's the right way to do it or not is arguable, but that's what they did, right? So the thing that we have to think about, where did these features come from, right? Because at the end of the day, your function approximator is implemented as a function of, see, at the end of the day, it is function of phi of s comma a and w, right? So at the end of the day, that's what it is, right? So your fees could potentially be learned. So you can combine everything and you can call it some g of s comma a and some w and theta, where theta is a function for learning phi and w is a function for, theta is a set of parameters for learning phi and w is a set of parameters for learning f, right? So you could think of it that way, but you need to have this kind of an intermediary feature computation, right? So how did this come from? We all know the answer. What is the answer? Sure, a deep network, right? So the original approach that actually tackled this Atari thing and kind of opened up the floodgates for all this new RL kind of work was called deep Q networks, right? So it's actually, if you think of it as deep Q learning networks, but everybody calls it deep Q networks or DQN. And so this was a paper that appeared in Nature in 2015, but even before that, it was presented as a paper at a workshop at NeurIPS, right, at the top machine learning conference, right? And I was actually there at that workshop when this presentation happened, and there was a lot of buzz, and some people were saying that, oh, this is great, amazing work, mind blowing, and other people were saying, oh no, this is okay, it's not a big deal, and stuff like that. And then during that conference, they announced that this group that had worked on this is now part of this company called DeepMind. They are going to launch this, etc., etc. So there was a lot of excitement at that time, right? So it's like you could see that something different was going to happen. Not that everybody bought into it at that point, right? So it's a complex, not a too complex a neural network given what we are using nowadays, right? It's basically this, right? So you can see this, right? So there was a input that's 84 cross 84. That was the number of pixels, right? The frame for Atari was 84 cross 84 pixels, and we used 4 frames. Remember, I was telling you why you need 4 frames, right? So you need to know whether the ball is moving like this or whether the ball is moving like this, right? So if I just show you a frame with a single ball, right, and you wouldn't know which direction the ball is moving. So we show 4 frames, and not just for the ball, right? So for whether the enemy is coming down or attacking, moving left, moving right, how you have to fire, all of these things, right? So all of this together, we try to infer that from just showing 4 consecutive frames, right? So the input, even though we are showing this as 1 frame here, right, but the input will be 4 frames conjoined, right? And then you have the first layer, which is a convolutional layer, right, 8 by 8 filters and a stride of 4 and totally 16 filters, right? And then layer 2 is again a convolutional layer. So this is layer 1, this is layer 2 is again a convolutional layer, and with a convolution size of 4 by 4 and a stride of 2, and we have 32 filters in this level, right? So that basically gives me the convolutional output. So it's a bank of 32 filters operating on the layer 1's output, and the layer 3 right, is a fully connected layer, right, with 256 dimensional fully connected layer, and that corresponds to, I mean, all of these are ReLU activation, right. And finally, you have a fully connected 18 dimensional output layer, right, where the activation is linear. So, why 18? Because if you think about it, Atari games, right, Atari games have 18 possible actions that you can take, right. Atari games have 18 possible actions you can take. So, there is one for doing nothing and one action for each of the 8 directions you can go, up, down, left, right, diagonally up, diagonally down. So, there are 8 actions that you can take, right. And then you could fire, do nothing but just fire, or you could move and fire, right. So, since there are 8 actions, 8 actions without firing, 8 actions with firing, so that is 16 actions, and do nothing 17, do nothing but fire, right, don't move but fire, that is 18. So, there are 18 actions. So, you have a output that has as many neurons as there are actions, right. So, remember I was telling you there are multiple ways in which you can do this. So, literally here you are feeding in S, right, and then you have 18 different outputs that is being computed, one for each action. So, this is Q. So, this will give you Q of S comma A1 all the way to Q of S comma A18, right. Remember we talked about the different ways in which you can set it up. I could have fed in S and A and asked it to spit out the Q values, but since anyway I will have to compute all the Q values when I do the max over Q, right. So, I basically feed in just the S and I get all the 18 Q values at the output. So, this S, basically this whole thing will be computing phi of S, and then finally I have the last layer, right, the last layer weights alone, right. From this fully connected layer going out to the weights, right, these weights are not shared between actions, all these weights are shared between all the actions. The final layer weights are not shared between the actions, so they are basically treated as 18 different function approximators. So, one way of thinking about it is this whole thing up till this point learns phi of S, right, and then I have linear function approximators. I have 18 linear function approximators, right, that output the Q values for the 18 different action. All of these take phi of S as input and output the different Q values. So, there are 18 sets of weights here at the output layer, each connected to one action. Of course, you are not going to treat it like this, you are going to treat it like a full network, and then you are going to have 18 dimensional output, right, and then you are going to train it based on the TD error. So, all of that is all fine, right. So, that's not an issue. So, remember the TD error training. So, that's how we are going to train it. Okay, is that clear? So, it's a very cool stuff, right. So, now we are building up the whole notion of function approximation. We said that okay, we have to do this with linear function approximators, right, and then we brought it all the way up to encoding a feature vector and then using gradient update rules with linear functions to train the Q values, right. And now we said, hey, come on, let's not design the features, let's use all that we know about convolutional networks and things like that, and design learn the features also. So, now I have a setup where I am learning the features phi of S, and then finally I have this linear function approximator. Okay. Now, the amazing thing with the Q learning, right, the DQN setup is that finally you are training only with the TD error, right. Remember that we had this, right, the regression loss. So, we used the TD error as the regression loss, right, because we did not know the true target, right. So, instead of training using something else, you are training just using the TD error, and that gives you the phi of S also. It allows you to do the feature learning on the input, right. So, you could think of doing this in a 2-stage process like you do sometimes in computer vision, right. So, you could just take a CNN and then you could have a CNN decoder, right, like you have an auto encoder, right, like you can have a convolutional auto encoder kind of a setup, right. So, the encoder and decoder setup, and then you could just learn the phi by doing that self supervised learning, right. So, you give the input and make sure you are able to recreate the output, and you could learn the phi, and then you could take that phi, right, add the linear function approximator on top of it, right. So, once this comes out, so you can take the so you can train it using the encoder, decoder setup, right, like you normally would have done with the autoencoder, right, encoder decoder setup, then remove the decoder, right, and then do a linear function approximator on top of the encoder, and then use that to fine tune the features and train everything using TD error. You could do that, right, but it turns out that the DQN doesn't need you to do this kind of end to error, this kind of feature learning. You can actually do this end to end just by using the TD error. So that's another amazing thing that the DQN setup gives us, right. So the whole training with just the TD error. Okay. Cool stuff, right. So we are not done though, and I'm going to look at this Q network learning, whether it is deep or non-deep, right. When I'm going to use some kind of a neural network, some kind of this regression based D squares kind of a setting, there is a problem. So what is a problem? Remember, we are using semi gradients, right. So that means that this thing we consider as a constant, right. This we consider as a constant target, but that is not a constant target, because this Q hat, right, it depends on the features or depends on the weights of the neural network that are currently computed, right. Therefore, my targets are non-stationary, right, my targets are non-stationary, right. So I'll have to somehow account for this non-stationarity of the target. Is there some way we can adjust this, right? That's one thing that we have to think about. The second thing is a slightly more subtle issue. This goes back to the fact that we are using stochastic gradient descent, right. So what did we do? We said, okay, we are using stochastic gradient descent, but because we are drawing these various samples over time, so even though if I am just taking one sample at a time, because I'm doing a good enough estimate of the gradient, everything will work fine, right. But what is really happening in the Atari game setting, if you think about the way the game progresses, right. So if you look at the first, when you start playing, right, the set of frames that you see will be very, very close to one another. The amount of changes that you see, right. So let's say that you have the Pong game, right, from one frame to the next, right. What will happen is this one pixel will move from here to here. Not a whole lot of change, right. So likewise, if you take any other game, right, because most of the pixels are dark, right, there are only few pixels that are lighted up. So the change from one frame to the next will be very small, right, and it will be seriously correlated, right. So it's like you're taking the same sample, almost the same sample again and again for computing the gradient, and therefore the gradient estimates can become very skewed instead of taking independently sampled data points, and therefore your gradient estimate is more robust, right. So instead of sampling just with one data, right, I'm just taking multiple things independently sampled, right. So my gradient estimate is robust. That's why stochastic gradient descent works, right. Now what I'm saying is, I'm not going to do that. I'm going to take this sequence of frames which are all looking very, very close to each other. So if I make a mistake in the gradient estimation, it will just get reinforced with the further samples, right, and therefore I have a potential of getting into this kind of a divergence, right. So instead of the neural network converging to a point, it might diverge. So this was actually one of the biggest problems that people had using neural networks earlier for Q learning, right. So it's not something that is peculiar to the DQN architecture. In fact, these whatever we are talking about now as fixes for the DQN architecture were introduced for multi-layer perceptrons, right. It is not something that was introduced only for the DQN. So what happened was, people had already come up with these fixes for simple multi-layer perceptrons. Now combined with the feature learning power of convolutional networks, allowed RL to solve more complex problems, right. So that's basically what happened. That's why I left out the deep part here, because even for any kind of neural network learning with Q functions and TD error, these problems were there, right. This guy Martin Riedmüller, who actually came up with a fix for this divergence issue, right. He identified these were the two key problems for the divergence to happen, and therefore he came up with ways to fix it, right. These are heuristics. Let's be very clear. The fixes that we are going to talk about now are heuristics. They are not in any way theoretically fixing the problem. They make the divergence issue manageable, right? So you actually get to something, right? There is no guarantee that you are getting to the right answer, but you converge to something because of the way we use these heuristics and manage the whole training setup, right? So what are the heuristics? The first one that he came up with was something called replay memory, right? So replay memory basically addresses the problem of correlation, right? So why was there a correlation problem? Because when we are actually doing the updates, we are taking the sequence of frames, right? And as we see each sequence of in the frames, we kept updating the Q value. So when we are computing the gradient, we are using successive frames, right? I mean, it could be a set of 4 frames, but we are using set of successive 4 frames, right? I mean, successive set of successive 4 frames. That's what we are using. So that still has a strong correlation, right? So to break that, he came up with this cool idea. So what did he say? Hey, anyway, we are going to do this kind of a mini batch learning, and anyway, we are using Q learning, so we don't worry about the trajectory, right? So I don't really need to update things in a trajectory because I'm going to use max, right? So what I need state, action, reward, and next state. I don't need the next action, right? So that's not needed. So I can take advantage of this. So what I'm going to do is when I come up, right, when I experience a transition, when I come to some state ST, I perform action AT, I go to next state ST plus 1 and I get reward RT plus 1. So I take this entire experience and put it into a buffer, right? Now, when I have to train the neural network, right, I don't take the ST, AT, that I don't take that tuple, I just go to this buffer and randomly sample a set of transitions, not consecutive, right? So I might sample one here, one here, one here, one here. So I just sample a set of transitions from this and create a mini batch of training with those transitions, right? And use that to update my Q function. Make sense? So now since I am sampling randomly over history, right? So these things are not correlated or less likely to be correlated because I am sampling randomly over history, right? To ensure that this correlation is minimized, they keep the replay buffer very large, right? So replay buffer can be like 1 million transitions or 2 million transitions. So when I'm going to sample say 1000 from that or 128 transitions from 2 million transitions at random, so obviously this is not going to have any correlation, right? So that is the idea, and the way I create the mini batch is I take the state, action, reward, next state, right? Basically I'll have the state action and then I'll have the Q target that will be there as the target, and I'll supply that to the mini batch, and that will basically compute what the gradient should be, and then I'll take the average gradient and make a change to the weights based on the average gradient that's computed given a mini batch. So this kind of breaks the correlation and significantly helps in the convergence. Of course, people have come up later, just like you had initially you had this 2-stage pre-training, fine-tuning kind of a process, and then people moved to end-to-end learning in deep learning. So likewise, people have actually come up with algorithms that don't need a replay buffer, but having a replay buffer is something that makes the convergence more stable, and so we still use replay buffer in many instances. Okay, the replay buffer takes care of one problem. So what's the second problem that we need to address? The target is non-stationary, right? So we need to address the non-stationarity of the target. So what we do there is something very simple. So remember, so the non-stationarity comes in because I am using the same weights W, right, for computing my Q hat, right, for computing the Q hat and for computing the max, right, the target. Right? So I am using the same weights W for computing Q hat and the target, and therefore the target changes whenever I change my weights, right? It's literally changing at the same speed as my estimates, right? As I keep changing my Q estimates, right, the estimates of my Q function, the target also changes at the same speed, right? So what they said is, no, let us slow down the speed at which the target is changing. So what will we do? So we will take the weights at some point in time, right? Let's say I'm started to update, right? Let's say I come to W100, right? So what I will do is I'll take the weights at W100 and copy it to something called W minus, right? And then I'll keep W minus fixed at W100 for another 100 time steps, right? So it will always be W minus until I come to W200. Then I'll make W200 as my W minus, right? And for computing the target Q value, Right? For computing the target q value, I will always use w minus and not w. So, w will be used only for computing the current estimate of the q, and w minus will be used for computing the target. So, what is happening here? The current estimate of the q is changing at every time step, but the target estimate is changing only every 100 time steps or every 1000 time steps and so on and so forth. Right? I could do this way also. Every 100 time steps or every 1000 time steps is when the target is changing. So, the target is changing much slower than the q estimates, right, and therefore, the non-stationarity is taken care of. It is not really taken care of, it is still non-stationary, but we know that if the target is moving slower than the actual estimate, the estimate will track the target and it will actually get there, right. So, this will allow you to achieve some kind of convergence, and therefore, again, like I said, it is a heuristic, right. So, this non-stationarity is addressed by using this Freeze target network. Nowadays, we do not use this Freeze target network often, we use some other kind of techniques for slowing down how much the target should, how fast the target changes, right. We use something called Polyak averaging. While the actual weights change much faster, the target weights change with a slower rate, right, by transferring more of the older weights into the newer weights. Okay. So, we will see that as we go along, right. So, but now, right now I am just talking about what the DQN people used, right. So, the Q network learning idea from Martin Riedmiller had both of these pieces in there, the replay memory and the Freeze target network. And the DQN people, Martin is part of the DQN paper, right. So, they kind of combined it with convolutional networks and then set up this training regime so that it could solve non-trivial problems like the Atari games, and doing this from scratch, right. So, how well does the DQN do, right? So, I will come back to this slide in a bit. How well does the DQN do, right? So, this is the set of Atari games which are considered the standard suite of Atari games, and this bars are some kind of a measure of performance, right, some kind of a normalized measure of performance. And so, what happens is, you can see this dotted line here, right. So, this any game to the left of this line, DQN was better than humans, right. Any game to the right of this line, right. So, here humans are better, right. Here DQN is better than humans, amazing, right. But nowadays what has happened is that line has shifted here, right. DQN is better, humans are better. There are maybe a couple of games in which humans still have an edge, right, but there are more complicated RL algorithms now that are competitive with humans even on some of these complex Atari games, right. So, it is like amazing how much progress we have made in the last 10 years in these kinds of strategy games, competitive games, and of course, we looked at a whole bunch of other applications of reinforcement learning. All of these started with this original DQN paper, right. So, just to summarize what happens with DQN, right. So, we have a set of convolutional layers. The original paper had 2 convolutional layers followed by 2 fully connected layers, and then later versions have 3 convolutional layers, and some of the later versions have gone crazy. And then some of the later architectures also have an LSTM layer after the convolutional layer, or LSTM layer before the convolutional layer. Instead of concatenating 4 frames, you use an LSTM to kind of summarize the frames and then feed that into the convolutional network. And there are other places where people have tried to learn the features and then do a LSTM to concatenate the features, and all kinds of complicated hierarchies architectures have come up, right. But the basic architecture was a set of convolutional layers followed by some fully connected layers, which gives you the final output. And remember, there are as many outputs as there are actions, right. And then you can compute the Q values here, right. So, you can use whatever you want. You can use epsilon greedy, or you can use softmax, right. I mean, if you have a neural network for classification, you always use a softmax on the output activation, right. So, likewise, you could use a softmax on this and then select a action to perform, and then once you perform an action, you will update the network through the output node corresponding to that action, right. So, one small thing that later people fixed was they used the Huber loss, right, not the regular least squares loss. So, if you know the advantage of that, right, so least squares loss, as the loss becomes slightly larger, right, it starts growing exponentially, while Huber loss actually grows linearly, right, for large values. right? For small values, it's fine, it's quadratic, but for large values, Huber loss grows linearly. So this bar, right? This is a linear growth. Therefore, if you have a large TD error, right, you don't get a corresponding large loss, right? So if the TD error is very large, then you kind of mute the loss. Now the Huber loss, then you have to think of how you would find the derivative and all that. So these are all common stuff, right? So nobody worries about this thing. So this is cool stuff, right? So now what has happened? It's come to a point where people don't even think about other forms of using reinforcement learning. Whenever you say I want to solve a problem using reinforcement learning, people just directly jump into one of the deep architectures, right? So the DQN is still a workhorse, and then we'll look at a few modifications, recent modifications for DQN, right? But then we'll also jump into a whole other class of learning algorithms called policy gradient approaches, and then actor-critic approaches. So there are three large classes of problems. So value-based approaches that we have seen so far, right? And then you have policy gradient-based approaches, and then you have actor-critic approaches, which kind of combines policy gradient and value-based approaches, right? And in fact, nowadays people don't do policy gradient at all, right? So policy gradient is always looked at it from the lens of actor-critic, and so we'll look at all of these, right?